So again, we're going to call this like a type 2 problem. So this is anytime the object is launched and lands at the same height. Now, this is going to allow me to introduce how trig factors into these problems without making the math so overly complicated that we can't actually solve the problem. So the real goal here is to introduce what happens when the ball is suddenly being launched at 50 degrees at 30 meters per second, and how that's going to change what we're doing. Now, there's a bunch here that I need to kind of throw at you, and I'm trying to be diplomatic here, but I want your notes to be more helpful than they've been to my students in the past years. So I'm trying desperately to make sure you're writing things down, that not just that I'm writing on the board. So the first thing I want to remind you about, that this hasn't changed the definition of a projectile. This object is moving in 2 dimensions, has an acceleration in 1. So when this object is launched, it's being given some horizontal velocity. And no matter where the object goes in its flight, it's going to have the same horizontal velocity. So in all those places, that arrow that's sideways doesn't change. Same height, same speed all the time. Now, the vertical does change, obviously. But in this case, it does start with a vertical velocity. Now you'll notice I'm drawing it to make the triangle over there. But for the rest of these, I'm going to draw the vertical velocity on the object. Go ahead, Kyle.
So it always has the same horizontal velocity even if there's air resistance?
Well, no.
Okay.
No, we're going to wait until we have more before we start talking about air resistance. Okay. So the object's vertical velocity is going to experience the same thing as when we just threw a ball straight upwards. You throw a ball straight upwards, it has a starting velocity, but the gravity is acting downwards on it, so it slows down. So after a few moments, its upwards velocity is going to be less. And then there's going to be a point where its upwards velocity is 0. And hopefully you guys kind of can recognize this is kind of an important place. This is where, it's going to be at its maximum height. If you're going to put something in your notes today about that, be very clear that this object will have a max height, just like an object thrown straight up in the air. And that maximum height will occur when its y velocity is 0. The only time we'll probably use the y velocity, the final velocity, is to find when the maximum height is attained. It's, should be kind of, not particularly weird that there's going to be a problem perhaps where we want to see if the ball can clear a fence, or if the golf ball can go over the tree, or if the baseball is a home run. You want to find out what the height is. That's not always related to the maximum height, but it's probably important that in your notes you know that the maximum height is when the y velocity is 0. That's worth probably highlighting, putting a box around. That the maximum height of a projectile is when the y velocity is 0. Now, of course, the object's going to keep coming back to the ground, so we're going to start building up that downwards velocity until just before we reach the ground, we're probably pretty close to back to where we started. So the difference between the projectiles we talked about yesterday and the day before and this one is that our velocity is going up and back down. So unfortunately, we're going to need to do a little bit different work than we did before. On the other hand, we're faced with the trig. And I don't think that's too big a deal. We've been talking about trig for a while. But that doesn't mean that it's something that you guys are super comfortable with. But let's handle the trig first. Because clearly the trig is going to tell us what the horizontal velocity is, and it's going to tell us what the starting vertical velocity is. Which means this velocity is neither one of those now. I'm going to call this the launch velocity because I have no other name for it, just v. It's none of the other velocities, it's the launch velocity. It's a 2-dimensional velocity. It comes with an angle. Now, you guys are practiced now with this stuff, so I don't feel like I have to spell it all out, but I'm not going to use the 30 or the 50 degrees right now. I'm going to do this as like a generic problem. And I'm going to say that sine theta is going to be equal to the opposite side, which is the initial y velocity, divided by the launch velocity. And this is the opposite side, this is the adjacent side. And I'm also going to say that cosine of theta is going to be equal to the horizontal velocity divided by the launch velocity. Now, this is the part that I hope you will kind of just accept. The initial y velocity is always going to be sine theta, and the initial horizontal velocity is always going to be cosine theta. Unlike other problems where you have to do the trig every time because it could be different, for projectiles, this will always be true. So much so that, like I said yesterday, you can just modify your chart and add it in here every time. This is v sine theta. This is v cosine theta. Every time. It was like that in the prior problems. The launch angle was just 0. So it always made the initial y velocity 0. So we can do it this way too, all the time. You can always count on that and just put it in the chart so you know to use it there. The problem itself doesn't change. It's still going to be a problem of us trying to figure out where the object is landing. And to do that, it's still going to be about finding the time that it's in the air. So we're going to do the problem the same way. I'm going to start by building a chart with a vertical side and a horizontal side. I'm going to list out all the possible things that might be here. But now I know that I have to figure out the initial launch velocity, the vertical and the horizontal. Again, I'm not worried about that. I think we can do it. We've got the launch velocity and the angle. So the initial y velocity is going to be 30 sine 50 degrees. And the horizontal one, 30 cosine 50 degrees. I'm going to use the launch velocity now because I don't have the individual pieces. Now, still going to decide that upwards is positive. I'm still going to decide that to the right is positive. That's going to make my acceleration negative 10 meters per second squared. But here's the part that I think is something I want you to use for this case. We're landing at the same height that we were launched at. So for these problems, delta y is 0. That's convenient. You can't expect that always to be true, but for the time being, while we're just practicing, yeah, I think that's a good place to start. Now, we're going to go ahead and execute this problem, but to do so, I need somebody to figure out what those two velocities are. So can we do that real quick? Somebody do 30 sine 50, and somebody do 30 cosine 50.
30 cosine 50 is 29. 30 cosine 50.
No cosine.
29? And what's 30 sine 50? 23? You guys should keep lots more decimal places. I can't fit them in there. Yeah. Go ahead.
I got 19 for velocity.
I'm literally looking at my calculator.
Is your calculator in degrees?
This is my friend's calculator, it's not mine.
It is 19. Yeah, it's 19.
It's my friend's calculator. That's not.
That's right, Kyle. That's right, Kyle. We're not changing your, we're not changing our opinion of you. It's still the same. So,
Thanks, JT.
good so far?
How do you do it?
Now, we're still gonna start by trying to figure out how long it's in the air for, and I still think that this is probably gonna be the best way to do so. And luckily, because there's a 0 here, it's not so terrible. However, you guys are gonna make a mistake here, and I really want to encourage you not to. You're gonna try and figure out how long it's in the air. And you're gonna get to a point where you're like this. Don't divide by t. That's not how math works. Factor the t out like you're supposed to, like your math teacher taught you. It's important for later that we do this correctly. Because if you factor the t out, like we're doing right now, you get 2 answers for t. And we're supposed to set this equal to 0 and this equal to 0. So the first answer for t is t equals 0. The second answer for t is 23 divided by 5. So 4 point something.
4.6.
The reason there's 2 answers is because that represents the 2 times when the object was on the ground. We asked the math to tell us when is the object's displacement 0, and it was 0 twice. Once at time 0, it was on the ground, and once later it was on the ground. Every quadratic is going to have 2 possible answers. You should always explore them. But I think we're going to ignore the 0. For this problem, we care about the fact that it was in the air for 4.6 seconds. That's the one we're going to use, 4.6 seconds. And I think that's how we're going to figure out where the object lands. 85, 84, 83. Somebody multiply those things out.
88.6.
88. Okay. 88 meters. For those who don't know where that came from, delta x is going to be 19 meters per second times 4.6. We're finding the range. Now, look at your notes. Just take a moment and look at all the things you wrote. I bet most of you have a whole bunch of numbers representing this example question. Do your notes tell you what you did? Do they give you enough information for the next time, or are they only useful because you did it just this minute and you can remember what all those things are? If not, perhaps you should talk about what you did. Right? First thing, I suggested you draw your chart. I don't care if you write these things down. It's just I want to make sure that your notes are helpful. The second thing, do the trig. All right, we had trig in this one. So the second thing we did was we did the trig. The third thing was recognize that delta y equaled 0. That made this a little unique. Right? We then filled in our chart. All right, looked at the up and down parts, looked at the side to side parts. We solved for the time. In this case, there was 2 of them. We used a time to find the range. These were the steps that we did to do this problem. You can see it if you're looking for it. But if all you have is a bunch of numbers and equations, you might not be able to get there. We solved for the time. What did we do? We used a motion equation. Right? That's how we solved for the time there. How do we find the range? Well, we did delta x is equal to Vx times t. Do you have that someplace to remind yourself? That's how you figure out what the range is. Now, there's more to this clear.